Hi guys, back with the math video. Today we're going to be looking at a geometry problem I think is sort of interesting. And the problem is, say that we have these regular solids, and we want to label the vertices of these solids 1 through n, n being the number of vertices on the solid. So for this tetrahedron, we could do 1, 2, 3, 4, like so. Make my thing a little bit thicker, or we can do 1, 2, 3, 4, stuff like that. However, when we label these vertices, we want each unique combination has to be unique in that you can't get two combinations or duplicates if you can rotate the solid in such a way to get that combination. So what do I mean by that? So let's say 1, 2, 3, 4. Let's say I have this, I label the vertices like this. Well, this labeling is actually the same as if I were to label it like this, because we just rotated the solid clockwise. So essentially those two labelings are duplicates. So again, this labeling is a duplicate of this labeling because we basically rotated this solid. So any rotations of the solid or movement of the solid in such a way that you can get another combination, those two labelings will be duplicates. So how many unique labelings can we get on the vertices of these solids? And is there an easy way to figure out the number of ways to get that? So that's the question. You can pause the video, try to solve it on your own, try to find out a formula that allows you to do that, and without further ado, let's go on to the solution. So let's think about this. So for a tetrahedron, let's start with the tetrahedron, right? So let's label it like this. That's obviously one combination, one labeling, one possible labeling. And we don't want to label it such that you can rotate it around and get the other combination. So I think what we can do is, instead of I think we can switch any two vertices, and this is another unique labeling. So again, this is a unique labeling, and this is another unique labeling, because you can't really rotate the solid such that you can't rotate. If you think about it like this, if this labeling is like this, right, and 1 and 2 stay stationary, you can't really rotate the solid such that 3 and 4 switch positions. So these two labelings are unique. And as it turns out, in the tetrahedron, there are only 2 unique labelings for the tetrahedron. Yes, so without further ado, I'm actually going to go on to the formula for the number of unique labelings, and I think it's pretty cool. So first of all, let's assume that how many total ways are there to label all the vertices without any regards for whether or not you can rotate the solid to get another labeling. I think if the solid stays stationary and you don't care about rotations, how many unique ways are there? Well, it's sort of intuitive. This cube has 8 different vertices, so the number of unique ways to label the vertices without regards to rotation would be 8 factorial. Now, for 8 factorial, this is the total number of ways, but for each of these number of ways, we've overcounted. We've overcounted because this labeling, right? This labeling would be different if we rotated the cube this way, and if we rotated it again, and we rotated it again, and we flipped it, and we did that sort of thing, and we rotated it. So we've overcounted each label by a certain number of times. And the question is, how many times have we overcounted that labeling? And I think we can count the number of times we've overcounted one labeling. Because let's say we have this labeling 1, 2, 3, 4, 6, 7, 8. We can count the number of times this labeling is overcounted by calculating the number of ways counting the number of ways that we can view this cube such that this labeling occurs. And what do I mean by that? I mean, we need to count the number of ways this cube can be rotated. And rotated and flipped over such that this labeling still holds true, but we're viewing the cube from a different angle. And if we count the number of ways it's true, we can actually find the number of ways we've overcounted. And there's actually a way to do that. That will apply to all regular polygons. What we do is we have one of the cube's vertices facing towards us. And what will happen is that it will look something like this. Right? So this vertex is faced, let's say this vertex is 1, right? And it's facing towards us. So we have these, right? And just having this vertex face towards us 1, how many ways can we view this cube in this orientation? How many different ways can we view it in this orientation, such that just by rotating this cube and flipping it around? Well, let's set this vertex towards us. This is towards us, coming out of the page, and we set this vertex as 1. If this vertex is 1, we can rotate this cube 2 other ways. So this will be, we can rotate it clockwise, so this will be 2, 4, 6, and this will be 7, 3, 5, and there's another way you can do it, and we can rotate it again. There's another way we can do it. So with the 1 facing us, there are 3 possible ways we can rotate this cube, such that all these labelings are the exact same. This is the same labeling because all we did was rotate the cube, and labelings where you can rotate it to get another labeling, all those labels are the same. Same labeling. So actually now what we can do is we can have a different number facing towards us. We can actually have 2 facing towards us. And I think what will happen is that if we have 2 facing towards us, 1, 3, 7, 8, and something, right? 6 and right? And then we can do the same thing again, and turn it clockwise, right? And do that thing and do it again. So when 2 is facing towards us, we can do the same thing. And oops. Oh, I sort of did it wrong, sorry. Just do that again. Right? So essentially, whenever we have a vertex that's facing us set, there are 3 ways we can rotate the cube so that there are these extra labelings. All 3 of these labels are the same if 1 is facing towards us. So there are 8 total vertices. So since there are 8 total vertices, we can have 8 different vertices facing us, right? And since we can have 8 different vertices facing us, and there's 3 different possible labelings for each vertex that's facing us, the total number of 8 times 3, 24, is the number of ways 1 labeling can be duplicated. So is the number of ways 1 labeling can be duplicated. So what this means is we've basically overcounted each labeling 24 times. And because we've overcounted each labeling 24 times, we have to divide 8 factorial by that. So actually I don't have the number with me right now, but that's how many. That's essentially how many unique labelings that this cube has. The cube has. For the octahedron, let's see what we can do. So with the octahedron, we actually can use the same strategy. So the octahedron has 6 different vertices, so 6 factorial, and then we choose a vertex that's facing us, and in this case it's slightly different because for each vertex that's facing us is 4 different vertices that's going out of it. So actually there are 4 different ways we can do this. So for each vertex facing us, there's actually 4 different ways you can rotate the cube to actually make duplicate labelings. And then there's 6 total vertices, right? So so that would be 6 times 4. It was 24. So 6 times 4. And So yeah, so actually I think we have a pattern. I think we can actually solve the formula right out. The formula seems to be the number of vertices n factorial divided by the number of vertices n, right? Multiplied by the number of lines coming out of that vertice. So for a cube, there are three edges coming out of a vertice. For octahedron, there are 4 edges coming out of a vertice. So number of edges from one vertice. And that's really the formula. So the formula just becomes sort of, actually it becomes more like n minus 1 factorial times the number of edges coming from one vertice. And that's actually a simple formula to find the number of ways of unique labelings for each regular solid. So actually we can sort of try it with we can actually try it with a tetrahedron, because we know the number of ways to uniquely label a tetrahedron. So it would be 4 factorial divided by 4 multiplied by, and there's three coming out of each vertice, times 3, which is 24 over 12, which is 2. So it works. So for the dodecahedron, it would be 1, 2. Actually, I can't count the number of vertices right now, but you get the idea. So that's the formula. I thought this question it's sort of hard to explain in words. It's one of those questions where you can't really explain it in words, but like if you have spatial reasoning and get it intuitively, it actually becomes sort of simple. And I think it's an important question that comes up a lot on in the AMC competitions, a lot of math competitions, like how many ways can you label is a really common question that comes up. So I think if you get this question, it's good for some future problems you might do. So I'll see you next week. Primes, and then this guy named Riemann comes in, and he's just like, well, I have a new function that I spent years in my basement working on, and the